Right, good day. Welcome to my online class. Please note that the content that I'm teaching here it's according to strength of materials and structures N5. Right. Today we will be checking the composite shaft or the compound shaft. So the compound shaft was just referring to a shaft made of more than one material, or made from different cross-sectional areas. It can be same material but different cross-sectional areas like this. Then this thing we're going to call it a compound shaft. So the compound shaft as well, you can call it a stepped shaft. So if this thing is arranged like this, then we'll say that this shaft is in series and end to end. Then if they are connected like this, then we'll say that this kind of arrangement or connection it's parallel. Therefore here we are going to look for components arranged in parallel and components arranged in series. So I will try to introduce both of them, and then at a later stage for this lesson or for this video we will only do either parallel or series. But right now I will start discussing the conditions of parallel and series arrangement. So this is the question paper that we are going to solve today at the later stage. So maybe let me start with parallel. I can divide this page like this so that maybe we can compare. Let's say this side it's for parallel arrangement. This side is for series. Series is when we have something like this. And then parallel, we've got actually three scenarios here for parallel. Okay, the first one, maybe you can have something like this. Certain material fixed to another material like this. Or second scenario, you can have a ring, something like this, which is this, and let's say it's a halo, something like this. And then inside this ring you put a solid shaft, or you put a certain materials like this, and then inside this you put this marker here. So this marker with my face will be, with my fist will be in parallel. So if you just put this thing right here at the end, then it will be series, end to end is series. But if you insert it to go through like this, then this fist of mine or this finger wrapped around this and this marker, they will be in series. So once this thing goes through inside, then they will be in parallel. So but once it's like this, they will be in series. Parallel like this is series because it's end to end. Right, so remember what's going to happen here is that we are going to fix this thing on one side. So we fix these things here. Then what we'll do is that we're going to apply a torque here You apply a torque there. Okay, the third scenario here for parallel, you can have this. Then maybe you apply torque there. So we will still consider this thing as a parallel. So even though that there is a contradiction with what we used to do, but this one, if you can check this one, there is not much difference because whatever that will be inside here, whatever that we're going to put inside there will be fixed to this wall. So even this outer one will be fixed to this wall. So it's the same thing. This component one will be fixed to the wall, and then this component, the other component will be fixed to the wall. The same thing here. Both components, two of them, they are fixed to this wall. So the characteristics of this will still fall under parallel. So the characteristics, I'm talking about the angle of twist and the total torque. They will comply with these parallel conditions. But if you remove one side, or let me say you say this, then we have another component. You don't fix it. You apply torque. Then that's where series comes in. It will be series. But if you fix both sides, then it will be parallel. So just be careful there. But even though that, I've never seen it in strength N5. So it was just for more information. Right. So what you have to know is that for parallel arrangement, the angle of twist in each shaft will be equal. Okay, let me just make some sense here. Let's say we have a ring like this, or a hub or a sleeve like this, and then in it we put another sleeve, or what else? Let's say maybe put a solid shaft. I don't know. Let's say we put a solid shaft. Either way. Then we're going to have a center here. Then remember, this thing is the cross-sectional area. It's like you have something like this or something like this. If you look at it from this view, you will have this red thing here, and then you'll have this transparent material here. So that's what you are seeing here. So if you draw a line here like this, straight like this, which is going to represent this, okay. So at this stage now, let's say that, okay, let me just use this since it's elastic. Let's have a line like this. Then from there, what we're going to do is that we're going to apply a torque. We're going to twist this thing like this. So when you twist this thing like that, that line now, it's moving to this side. Sorry, it's moving like that. It was here, it was straight before the twisting. It was like this. But when I twist this thing, that line moves, as you can see. So that line will move from there, maybe to there. So this line, undeformed line, and this deformed line, so we can say this is undeformed deformed line, and this is what we call deformed line. So this undeformed line and deformed line, when they will meet somewhere there, they will form an angle. So the angle that will be formed there will be the angle called the angle of twist. So this will be the angle of twist. So what we are saying here is that this solid shaft, which is inside together with this outer shaft, they will both twist with the same angle. So maybe let me just try to make something here. Let's consider this outer material first. Let's consider this portion here. If you consider that portion there, you will have this. This is for maybe let's say shaft 2, shaft 1. Then if you project this line like this and this line like this, where these two lines meet, there will be an angle formed. That angle formed will be what? Will be the angle of twist. So this angle is the same as this angle here. Then if you consider shaft 1, then you will have this thing. This portion here is this one here. So we're saying that this angle will be equal to this angle. So this is the angle of twist considering the outer shaft. They will form this angle. These two lines will form this angle. And then if you consider this solid shaft, which is this part here, the angle formed will be this one. So this angle will be equal to this. If in mathematics we say that this angle is common. It's common for this kind of triangle and common for this big kind of triangle. Therefore, the angle of twist for this outer shaft and the inner shaft will be equal. So in that way, we say that this angle here, we can say it's total angle, or we can say it's the angle of twist for shaft number 1, or we can say it's the angle of twist for shaft number 2. They will be equal. Right, condition number 2 is that, let me write it here, total torque composite, is it the right spelling? Hopefully, composite shaft is the sum of what? Let's say sum of torques transmitted by each individual shaft. Now we can say that the applied torque, let's say applied torque is shared between shafts in series. So if you apply a torque here. Let's say that torque is 10 kNn. Is this drawing it? Okay, let me say this. This green one is the solid shaft. Then there is this one. Okay, this is the cross-sectional area of this. So if you apply torque there of 10 kNm, so this shaft, remember the function of this shaft is to transmit the torque, is to take the torque from one position to another point. So actually here in reality we might have a certain machine there. We connect this shaft to a certain machine. It's not like we're going to fix this thing to the wall. It's not like that in application. Okay, so we have motor or engine here. You have to take that rotational torque, that rotational energy. We want to transfer it to the gearbox or to the diff, or if you have a high keel. The function of this shaft is to take that power from one point to another point. So we say that if we are transmitting the torque that you apply here is 10, then this shaft, this maybe sleeve 1, the hollow one is going to transmit, out of this 10 is going to transmit 7 kNm, and then this inner one out of this 10 is going to transmit 3 kNm. So these two shafts are going to share that torque. So these individual shafts, they will transmit a share of this torque to the other side. So in that way, we say that total torque, which we are referring to this 10 now, the torque that we apply, they will be equals to T1, the torque that will be transmitted by shaft 1, plus the torque that will be transmitted by shaft 2. Right, you can relate this thing with when you apply the force axially. Okay, I can use the same space. When you apply a force like this, axial like this, remember this force will be acting parallel to the length of this. Then in that case, this force is going to have the impact of stretching this, the length of this. Therefore, that's where we had this thing of X. But we know that in series, this is parallel. So if we have a parallel arrangement like this, we know that these two components, they are going to share the load. In parallel, we know that Ft equals to F1 plus F2. We can relate it with this part. Ft equals to F1 plus F2. In parallel, they share the load. And then in parallel as well, when this thing expands, these two material expands, they will expand with the same length or same extension. They will expand with the same magnitude there. Then we know that in series, X total equals to X1 equals to X2. So remember here, we're dealing with twisting. So this torque, you can relate it to a force. Remember, torque is a turning effect. The turning force, it's a torque. And then this one is the change in length, or is the deformation, this one, this theta. Remember, if you pull this thing like this thing will move from here to there. But if you twist it like this, the deformation that will occur there, the deformation will be in this manner, in this direction. This line or the material that was here will move from here to there. The material that was here will move from here to there. The material that was here will move from here to there. The material that was here will move from here to there. So this is you can relate it to the change in length. It's just that this change in length is going to form an angle like this. So you can relate this theta with what? With the change in length. Right. In series is going to be the vice versa of this. In series is going to be the vice versa of this. Okay, you can relate it with that part of axial loading. If we apply the force like this in series, we know that the force that you apply there will be common. They used to say F1 equals to F2, but in this case of applying the torque like this, we'll say T1 equals to T2. So the torque that will be transmitted by this will be equal to the torque that will be transmitted by this. So the same thing for axial loading, then we used to say that total extension equals to x1 plus x2. Then in this case, we'll say that theta total equals to theta 1 plus theta 2. Right. Then from there, we know that at some point from that axial loading thing, we used to say F equals to, X equals to FL over AE. In this case, we are going to have this kind of formula. Theta equals to 10.2 is there on a formula sheet. I've also derived it from the first lessons over GD to the power 4. So now in most cases, instead of using this, when we consider torque, we're going to have this for theta. Right. I can try to make some sense here. Okay, let me just draw something like this. Like this. So it's something maybe like this. So I'm trying to go to that part of total torque. So by applying the torque on this end, you are going to have this. So this line is no longer straight now. It was going like this. It's no longer straight. So it means that this first portion, it's going to have an angle of twist. But this line here is not yet twisted. This line is still straight. It's still straight. Therefore, but what you'll see is that as you move this thing from here to there, this one as well will move from here to there, even so that it won't be twisted. Okay, remember this thing initially it was like this. So what I'm saying is that when you rotate this thing like this one here is also going to rotate. It's going to move from this to somewhere there. So when you rotate this thing like this, it's moving. This line is moving, but it's still straight. But it was initially here. It's going to move from here to there. So that's why I'm saying that this thing is going to move from here to there. from here to there by twisting this one. So again, when you twist this one like this, now this material is going to move from here to there, to somewhere there. So now this will be the angle of twist for this shaft too. So the total angle of twist now will be this, like this. This will be the total angle of twist. So this total angle of twist, you will measure it from here to there. So you will see that the angle of twist from here to there will be given by this. Initially it was diagonal, there is this angle here. So this angle will be equal to the angle of twist due to this. And then from here to there will be the angle of twist due to this second portion. Therefore, that's why we said that the angle of twist here will be equal to the angle of twist 1 plus the angle of twist shaft number 2. So you just have to know this. So that is the only new thing that we are coming with in this chapter, but you can relate. Okay, back to that question. Steel rod fits concentrically through a cast iron tube. So get this scenario. This scenario. We are going to have a steel rod that is going to fit inside the tube. Your tube will be like this. And then we're going to feed a rod. A rod is something like this. You are going to feed this thing. Okay, let me draw it here. This is your rod. We're going to take that into that. Then we're going to have the parallel. It fits concentrically, so it has to go through. The rod and the tube have plates welded at their ends, so they form one complete unit. Oh, one other thing that I forgot to mention is that for this theory to exist, this one and this one, they must be rigidly fixed. So this component, this one, they mustn't be loose, they must be rigidly fixed. Alright, the steel rod has a diameter of 7 mm, cast iron tube has inside and outside diameter of 12 and 17. Okay. This will have inner diameter and the outer diameter like this and like that. They gave you the dimensions. They also gave you the dimensions of this rod. You will have 17 and 12, and then you will have a 7 here. So even though that there will be gap in between 12 and 7, but remember they will be welded, so they will be fixed. They will be welded at the ends. Right. The rod and the tube are of equal length, all right, 250. A modulus of rigidity for steel is this, a modulus of rigidity for cast iron is this. So calculate the stiffness of each material. So to calculate the stiffness, you've got 2 options. You've got 2 options. You can calculate it using this formula. Here's the formula for torsional stiffness. So it will just depend on the information given or the type of information that you'll have at that stage. Right. From what we have, then we can use this. 2.1, we have to calculate stiffness. Stiffness of each material. So we can say C equals to G J over L. Remember, it's from here. Okay, let me just maybe write this formula in full. Stiffness equals to T over theta equals to JG over L. So we've got the pipe or that hollow shaft. What did they say? They said it's a tube. Okay, we're going to have a tube and the rod. So we're looking for stiffness of the rod. Let's say rod, and then the stiffness of the tube. So we'll use the same formula, GJ over L. The only difference, okay, rod is made from different material, then it will have a different value of G, and then tube is different material than the, remember this G is about the resistance of the material, so it depends on the type of material. So since the material is not the same, we've got steel and cast iron, so these G's won't be the same. So these ones as well, I don't know, maybe you can start by calculating them, or you can just calculate them at the same time. Okay, let's maybe do it once, I don't know. But I think for max purposes, you can calculate them separately. So like this, you can say J. Okay, actually let's consider one material here at the time. Let's start with steel. They say it's the steel rod. Consider steel rod. Then let's calculate the J for steel rod. So J will be, remember the rod is solid. We're going to have pi d4 over 32 equals to, or you substitute there, the diameter for the rod is 7 millimeter. Due to time, I'm not going to press calculator with you, but you will get this. Then from there you can calculate what that stiffness for the rod. This rod is made from steel material. That's why they said that a steel rod. Then that means the G here will be the G for steel, which is 80. It will be G for steel, which is 80. Then you will have 80 times 10 to the power 9. Multiplied by J is this one, 2.357. Over L, length is 250. You convert it to meters, you will have 0.25. Then that will be equals to 75.424. So that is the stiffness. What is the unit here? Okay, I'm checking the unit for stiffness. I don't see it, but it's let's say it's this, but I will confirm it later. I will confirm it later. Okay, let me quickly check if I can find. Yeah, it's right. It's correct. Remember, this thing is from where? It's from here. Remember, stiffness is torque over theta, the angle of twist. So the unit for torque is this, Newton meter, divided by the unit for angle of twist is radian. So that's why we have Nm divided by rad. So that unit is from there. Yeah, it's correct. Then now let's consider the tube. What did they say? They said cast iron tube. So let's consider cast iron tube. So you do the same thing, J for cast iron. Remember, this one is a tube now. In other words, it's a hollow. Then you will have this big diameter squared minus small diameter to the power 4. The outer diameter is 17, inner diameter it's 6.164 times 10 to the power minus 9 m to the power 4. Then from there you can calculate stiffness. Using this formula for cast iron, Ci, cast iron, cast iron tube. Okay, you can use Ci, it's fine, but maybe we're supposed to use tube because here we're using material. Now here we are using the profile. So maybe if you stick to profile, then let's say tube, tube. Okay, it will be Jg over L equals to, now for G we're going to use the stiffness for G, which is 32. 32 times 10 to the power 9 times this. All over L, they've got the same length. The tube and the rod, same length, 250 millimeter. Then you should get 788.992. Right, I think we are done with question 1. Stiffness of each material. Question 2, the total stiffness for each compound shaft. So now we're looking for stiffness of the compound, of the whole thing. So the whole thing we're referring to this tube together with this solid shaft fitted in it. Therefore, now to get the total stiffness of this, we're going to add them. But this thing is from here. Let's say 2.2. This thing, it's from here. It's from the fact that in parallel, remember in parallel, T total equals to T1 plus T2. Then if you take this, you divide this by theta. Divide by theta, divide by theta. So remember, mathematically, there is nothing wrong here. Whatever that you do on this side, you must also do it on this side. So I divided this thing by theta. I divided these two of them by theta. So if you do that, then you will get this. T over theta, remember, T over theta is what? Is the stiffness. Total stiffness we are referring to the stiffness of the compound or of the composite will be this. And then now to calculate the stiffness of the compound, you just have to add those two answers that you got from the above. Then we'll have 75.424 plus 788.992. Then you will have 864.416. So that is question 2.2. Question 2.3. Compare the stiffness of the solid shaft with the stiffness of the hollow shaft. So provide the ratio. So we're going to compare the stiffness of this solid shaft and the hollow shaft in terms of the ratio. So there it's really up to you, or divide which by which. The ratio, we're just referring to a certain value, similar variable divided by a similar variable. So if it's length, you take length divided by length, then we'll get the ratio of the length. If diameter, you take the diameter divided by the diameter, we get the diameter of the stress. So if here is the stiffness, then you just have to take the stiffness divided by the stiffness, and that way you will get the ratio. Right. Then it's really up to you to whether start with which one divided by which one, but anyway we can say the stiffness of the tube divided by the stiffness of the rod. You will have what? You will have stiffness of the tube is what? 788.992 divided by 75.424. Yeah, hopefully you'll get 10.491. So that is the ratio of these two stiffnesses. But to make sense, you can simply from this equals to this, make this the subject of the formula. Then we can say the stiffness of the tube equals to 10.491 times stiffness of the rod. So that is the relationship between the two. So you can put it in that way. You can say C or if you turn them around, you can say C rod over C tube 1 into 10.491. So the stiffness of the rod goes 10.49 times into the stiffness of this tube. Okay, anyway, we're done with that one. 2.4. 2.4, the angle of twist for the compound shaft when a torque of 3 is applied. So remember, we know this thing. Theta 1 equals to theta 2. So now we're looking for the angle of twist, but remember your approach will be guided by the information given. So if you check here on 2.4, they gave us this value. So we're going to apply the torque of this much here. So that will be the total torque now. So if we've got that total torque, then we have to take, our approach will have to be from there, from the data given. So because they gave us this, then we have to use it. Then we know that total torque will be equals to torque in shaft 1 or in tube plus torque in shaft 2, which is that rod. Then according to the formula you can make, remember these formulas, these things, they still work. Torque equation, Tj equals to G theta over L. So if you make torque the subject of the formula from here, you will have what? You will have T equals to G theta multiplied by J over L. So we're going to replace this torque by this. Then you will have G theta J over L for tube. You'll use data for tube here plus G theta J over L for rod. You'll use the data for rod there. Remember theta in parallel. This theta and this one, they are the same. They will have the same value. Then if this one equals to this mathematical, what we do is that we take that value as the common factor. So it's the same thing with this one. You can take it out as the common factor. But since we'll be looking for theta, then there is no need to take out this one as the common factor. Then remember, total torque is 33. It's given 33. Is it Nm? Yeah, it's not K, it's Nm. Will be equals to, I'm going to take out this theta as common factor since it's the same. Then you will have G. G for tube. G for tube is 32. Then we'll have J. Then for rod, then you make theta the subject of the formula, then you will get 0.0382 radians. Then you convert that angle to degrees. Did they specify the angle of twist? Since they didn't specify, you can leave it in radians, but if you want to write it in degrees, then you will multiply it by 57.3 or by 180 over pi. Then you will get 2.187 degrees. 2.5, the torque transmitted in each shaft. So from this equation, you can still use this equation. Yes, you can use this equation. From this equation, actually those torques are these values. You just have to take this. Remember, this is torque, this is torque. So this multiplied by this is torque. You just have to take this thing multiplied by this theta. We've got the theta now. Okay. For torque for the tube, still the same thing is this. You use this. J theta J over L. G is 32. Theta is this, 0.0382. J is this. Over L is 0.25. Yeah, you should get calculate there. $30.097. And then for rod, it's this one, J theta J over L. Use this, 80 times 10 to the power 9 by 2.357. Multiplied by theta. Remember, this one is just G, this one is J, then we are left with theta. Theta will be 0.0382. Then you should get 2.877. Remember, when you add this one and this one, they should give you that 33. Torque for tube plus torque for rod, when you add them, they must give you 33. This one plus this one must give you this. Right, 2.6, the maximum shear stress in each material. So we're going to use the very same formula, torque equation. We can say T, or is what? Question 2.6. Tg equals to shear stress over R. Then we're looking for shear stress. Shear stress equals to TR over J. Let's start with, let's say, tube. Torque for tube, we got 30 times, or sorry, 30.097. It's not K, it's just NM, multiplied by R. The radius, I've said that always you use the outer radius. In other words, you take the outer diameter divided by 2 from the tube, remember we've got 2 diameters. What is the outer diameter there? The outer diameter was how much? 17. Yeah, then you'll take that 17 divided by 2, 0.017 divided by 2. That will be the radius. And then J, we calculated the J's at the beginning. J for tube, it's this 6.164 multiplied by 10 to the power minus 9. Then from here, you calculate shear stress. You should get 41.5 MPa. Then now you go to rod. Torque radius over J. Torque for rod 2.877 multiplied by radius of the rod. So if you have a rod like this, the maximum shear stress will be here at the outer diameter. So this diameter, use the distance from here to there. So use the diameter of the rod. So since we're looking for the shear stress in each material, so the shear stress here, use the distance from here to the diameter of the rod. It's 7. Then you will have 7 divided by 2, 0.007 divided by 2 over J. J for rod, (2.357) times 10 to the power minus 10. You should get 42.7 MPa. The last question, 2.7. The power transmitted when the shaft rotates at. We know the power formula is 2 pi nt. It's over 60 if this n is in revolutions per minute. But this time, this thing is the standard unit. Actually, they gave us this angular velocity. They gave us this. They gave us this. This is the angular velocity. So the angular velocity, the unit for angular velocity is rad per second. So for n, it's revolutions per second or revolutions per minute. So by checking this unit, it tells you that value, 20 pi, is not a rotational frequency. It's the angular velocity. Then from that equation of power, we know that if we've given the angular velocity, then power equals to angular velocity multiplied by tau. Yeah, but anyway, I was saying here, if this n is in revolutions per minute, then we divide by 60. If it's in revolutions per minute, then you'll just use this 2 pi. You can use small nt. If n is in revolutions per second. If n is in revolutions per minute, to use this. Okay, but anyway, it's fine here. They didn't give us n, they gave us angular velocity. Then we just have to say power equals to 20 times pi multiplied by torque. So torque, we use the torque of the shaft. The shaft we're talking about, the whole shaft. Those two shafts combined, they will form one shaft. So those two shafts, they will have to carry, or they will have to transmit the torque of 33. So the torque, that will be the power that will be transmitted by this power, by this shaft, by applying a torque of 33 on it. The power that will be transmitted will be this, provided that the speed is 20 pi rad per second. Right, thank you very much, 24 marks. Yeah, I don't think it was a difficult concept. You just have to know the basic torque equation and know these conditions for parallel and series. Thank you very much.